Okay. So we're gonna go through two PowerPoints today. Um, this first PowerPoint is where your assignment comes from. So just a reminder for you of where we are headed this week. If we go to our classwork tab, if it lets me load it, which it doesn't look like it's going to. If we go to our classwork tab, your week 5 assignment is this energy in chemical reactions assignment. So we'll talk about this again. This is derived all from this first O5 PowerPoint, and then the second O6 PowerPoint here. This is a really short example, just looking at how we can intercorrelate moles and heat. So starting off with this first PowerPoint, heat in chemical reactions, exo and endothermic. Many of you likely have experience with exo or endothermic reactions. You just weren't aware of that terminology before. Basically, exo and endothermic reactions, exothermic means that energy is being released or heat is being given off. And so that would be something like if you're boiling water, heat is being given off in the form of steam. You're feeling that heat coming off of it. That would be an exothermic process. Endothermic would mean something is slowly but surely getting colder. It's absorbing heat from somewhere else in order to get colder over the course of time, or it's absorbing energy in order to get colder, is what I meant to say. So, all chemical reactions involve energy changes, whether energy is being absorbed or given off. And what is happening with the energy is that it's being stored in chemical bonds. And the phrase for those is intramolecular bonds. Intramolecular bonds. That means within the same molecule, holding the different atoms together are these intramolecular bonds. And that's where all of the energy of each of the atoms is stored. And that's where we can have these exothermic or endothermic reactions. The bonds that hold molecules to each other are called intermolecular forces. So if you remember our little penny example that we did, where you could form a glob of water on the top of that little penny, you could use our little droppers and you could form water in the form of a bubble on top of that little penny. Those would be intermolecular forces. In other words, the water molecule is attracted to the water molecule. That would be an intermolecular force. Intramolecular force would be like this. It would be these bonds. These would be intramolecular forces. All right. And so when we keep going, we study heat and we use the term enthalpy to actually study the energy changes. So, enthalpy, which is this H degree symbol here, is the heat content in a system or the total amount of potential and kinetic energy within a substance. And we measure that in joules. So, what's worth noting is that this degree symbol here represents something called STP, which is standard temperature and pressure. Standard temperature and pressure. And what is known as standard temperature and pressure is 25 degrees Celsius and 101 kPa, which is just looking at the pressure um, based on where you are located on the Earth. You'll notice some of the questions that you've been given have said this like 25 degrees Celsius. What happens when this reaction is done at 25 degrees Celsius? That's just saying that it's done at standard temperature and pressure. So 25 degrees Celsius and 101 kPa is where all of the reactions and all of the energy and heat exchanges that occur, that's the temperature and pressure that everything has been measured at. And so that's what that little degree symbol after the H is showing. And so the enthalpy of the reaction, that comes from two different things. It comes from the bonds that hold the substance together and also the motion of the particles. Atoms very rarely sit absolutely still. We said that the point when atoms are absolutely still and they are no longer moving is at minus 200 or at 0 Kelvin or minus 273 degrees Celsius. That's called absolute zero. And that is the only time when the molecules or the atoms will stop moving around and stop generating energy. So we can't measure the enthalpy of the system. We cannot measure that. However, we can calculate enthalpy changes during a reaction, and we call that delta H prime. And one of the things I want to clarify about this delta symbol is whenever you see this delta symbol in a reaction, what you're doing is you're taking the something final and you're subtracting something initial. So when we were doing Q is equal to MC delta T, I didn't clearly say this, but what you're calculating is Q is equal to MC multiplied by the temperature final. So at the end, what was the temperature minus the temperature initial? So an example of that would be, let's say something cools from 20 degrees Celsius to 5 degrees Celsius. In that case, your final temperature that was arrived at was 5 degrees Celsius. Your initial temperature where it started was 20 degrees Celsius. So that's what the delta symbol means there. And so similarly with enthalpy, we want to calculate the H degree, the enthalpy final minus the H degree enthalpy initial. That's the end goal of what we want to be able to calculate. And we call this change, this is a really key point, we call this change in enthalpy the heat of the reaction. So first we're going to look at exothermic reactions. Reactions in which there is a net release of enthalpy. This is when enthalpy is released, an energy term will appear in the product side of the equation. So similar to the reactants in products, this value here will occur in the product side of the equation. Now there's two different ways that you can write and represent this. You can include it as like this, like a plus 847.6. Or the other way that you could write this exact equation is you could do Fe2O3 plus 2Al goes to form Al2O3 plus 2Fe. And then on the side, you would say delta H is equal to negative 847.6. And then our units for that is kilojoules. We'll talk about this in a sec, but if something is on the product side, if something is an exothermic, if it's an exothermic reaction, heat is being released, or you can think of it as heat being lost. And so our delta H value will be negative. Anytime we have an exothermic reaction, the delta H value will be negative because we are losing or we are releasing heat. So again, this little word equation says the thermite reaction is a highly exothermic reaction between iron 3 oxide and aluminum, producing aluminum oxide and molten iron. Because it's exothermic and releasing energy, we would put this plus 847.6 on the product side, or we could write it as I have written up top here, where you have the equation, and then you have on the side delta H degree is equal to negative 847. In this particular equation, your hand would get warmer if you were to hold it above the reaction that was happening. Again, it's releasing heat, meaning that heat can travel to you. So recall that in an exothermic reaction, releases more energy to form the bonds in the products than it did to break the bonds in the reactants. So again, we have an exothermic reaction here where one of the products is 220.1 kilojoule. The other thing that's interesting is we do not need to balance this number. We do not need to balance this number. That is the number for the reaction. So we do not need to actually balance that and multiply it by 3 or put a coefficient in front of it at all. Exothermic reactions release heat because the reactants have a higher heat content. So the reactants here have a higher enthalpy than the products do. And so these graphs, we will look at them a ton if you're taking Chem 30. You will look at these graphs a ton. Again, we said that the delta H, the enthalpy, we said that heat is being released. Heat is being released. The other way I described this is I said you will have an exothermic reaction with a negative delta H value. And the reason that delta H value is negative is because these graphs have been developed. So down here it says that this is the reaction pathway. So as the reaction is progressing, you can see that the delta H, or the potential energy of this, is going down. We're losing delta H. And so as such, we would say that this delta H value has gone down. In other words, it's negative. We've lost delta H. So that's a graph for an exothermic endothermic reaction. Again, you can see the reactants turning into the products over the course of time. This graph shows that the amount of potential energy in the reactants is more than the potential energy in the products. Again, we said that's why it's an exothermic reaction. This is like rolling a boulder down a hill. As the boulder goes down, it loses potential energy. Exothermic reactions tend to be a lot more spontaneous, meaning they can happen randomly, than endothermic reactions. So, if you've ever heard of something called spontaneous combustion, I was warned about that a lot in my IA class, again, because of the varnish that you put and some of the paints as well that you put on some of your wood products. That is an exothermic process of you actually putting the varnish on the wood product that you have. And so when it releases heat, if it releases enough heat, it can cause the wood to spontaneously combust. And when that happens, everything catches on fire. And then the little Chucky meme from The Simpsons, I'm in danger, appears, and it's real life. So we can remove the energy from the equation and record it as a change in enthalpy. This is the second way that I had showed you you could record this. So these are two separate parts. This first part is the reaction. The second part shows the negative delta H. So the heat of the reaction above is negative 220.1. You'll also notice that that reaction is the exact same as this one with this 220 recorded on the side. This last point is kind of important here. It says the heat of reaction above is negative 220.1. We describe the reaction by saying that in the formation of 1 mole of CuCl2 from 1 mole of Cu and 1 mole of Cl2, 221 kilojoules of this was released. So we do not need to balance this number. However, if I were to say that 2 moles of this entire reaction were to occur, I would also need to multiply this number by 2. If 2 of this reaction were to occur, I would multiply this number by 2. This is just 1 mole of the reaction happening is equal to an enthalpy of negative 220.1 kilojoules. Again, if 2 of these were to happen, I would multiply that by 2. So that's exothermic reactions. Exothermic was the release of heat. Endothermic, which is we'll talk about now, is the absorption of heat or the net input of enthalpy. This is indicated by writing the enthalpy term on the reactant side of the equation. Consider the reaction when sulfur trioxide decomposes into sulfur trioxide and oxygen. This reaction requires a net input of energy. And so as such, because it requires energy for this reaction to actually occur, it appears as a reactant. If you held this reaction in your hand would feel colder because the energy required for the reaction to occur would be taken from the surroundings, in this case, your hand. If any of you have tried to do put ice or ice water together and then you pour salt in it, you'll notice it gets quite a bit colder. And then that is the exact example of an endothermic reaction. It is absorbing heat from the surroundings. And so if you have ice water in a glass and you put salt in there, it'll actually get colder. It's absorbing heat from the surroundings. And so your hand on the side of the glass would feel colder. Likewise, endothermic reaction requires the addition of energy, and this excess energy is stored as the bonds of the product. So these two products will have a higher enthalpy than the actual reactants will, and that's why it requires the input of energy. We say that the enthalpy of this system is increased. Again, these guys have higher enthalpy or heat than the reactants did. So this is the endothermic graph. If you compare the two, the exothermic graph looks like this. The reactants have a higher delta H than the products do, indicating that we are releasing heat. Here, the reactants have a lower delta H than the products, indicating that we are absorbing heat. And so what that means is that for all endothermic reactions, delta H will have to be a positive value because we are absorbing more heat. For endothermic reactions, delta H will be positive. So the comparison here is this is like pushing a boulder up a hill. It takes energy to do so. You cannot simply just roll it down the hill and it'll spontaneously happen. This requires a massive input of energy in order to actually roll that boulder up the hill. And then we can remove the energy from the equation and call it as a change in enthalpy. Again, this is the second way that you can demonstrate this. I don't care. I don't have a preference over which way you actually demonstrate it as a separate reaction or as in the actual equation. I think doing it in the equation is easier. If it's exothermic, you know that it's being released and you can just record the plus delta H over here if it's exothermic. If it's endothermic, you can just include the plus uh, certain number of joules over on the reactant side. The reason that I think it's easier is then you don't have to worry about the sign. You don't have to worry about whether it's positive or negative if it's exothermic or endothermic. Either way is fine. I think doing it in the equation is easier, but you might think otherwise. All right. That is our first little part of the lesson today.